Now, reverse mode AD, which is essentially a generalization of backpropagation. It was invented before then, long and interesting history. Read the Biden's paper for just the starting moments or the starting points of that history and the pointers. But let's go and choose only one way how we can talk about it right now. But just have in mind it's live and it's very versatile and much more interesting than a textbook or tired professor can tell you about. You have to explore for yourself or just have in mind, just don't fall into narrow-mindedness um, point mode of thinking. Reverse mode ID. So in the 1970s, tools for automated generation of adjoint codes, also known as reverse accumulation mode, automatic differentiation, also known as backpropagation, were developed. Uh, Here's some history. Type 1, geniuses transforming mathematical systems. Gauss, Feynman, Razanauer, and Panchagin, so back as far back as 1931 and 1959. Yeah, surprisingly, Feynman in 1931 discovered something that is a derivative through a fixed point. A lot of interesting stuff. Type 2, a little later, manual transformation of computational processes. Bryson in 1962, Verbus in 1974, and LeCun in 1985, and then later Rumelhart in 1986 found specific ways how to code the differentiation. You can write a code that will differentiate your specific computational process, or you write a computational process that is computing derivative of your computational process. That's what we used to do when we manually coded backpropagation without, well, I did um, long ago, but anyways, but also not long ago, very, very, way after uh, um, from the after the time when automatic type 3 computer programs that transform other computer programs were invented. Spielpenning, 1980s, published the truly first system that automatically does everything one needs. So Lush, due to LeCun and Leon Bottou, and its predecessor, 1988, SN, I think, already had that built in as well. And then Type 4 uh, programs, it's when AD operators are first class and they have closures and everything. So things like Stalingrad, R6 RSAD, Autograd, diff sharp, and others. So the type 4 is truly differentiable programming when you're in control. First class AD operators, just imagine. So Bert Spilpenning, here's our hero. 1980, right? Compiling fast partial derivatives of functions given by algorithms. That's what he did. So in Fortran, he implemented a system, as we see here, called Jake. That major result of this research would be a full solution to the problem of compiling fast gradients has been obtained. For the problem of compiling fast Jacobians of arbitrary shape, a partial solution has been found. This thesis describes a method and its implementation capable of producing algorithms AF sharp that compute the gradient of a function f of x1 through xn in an amount of time equivalent to a constant number of function evaluations independent of n. The space requirement of the algorithms are modest. That's important, by the way. That is important. Space requirements. So here's a little more interesting stuff that Bert is writing, Bert Spilpenning is writing there. The separation of numerical analysis from software is virtually complete. That's 1980. And a few people care to bridge the gap between the areas. In numerical analysis, the notion of programs that produce programs rather than numbers is largely absent. Conversely, people involved in writing software tools may have a tendency to write only such software tools that aid in the writing of other software tools. What seems required is, well, sorry, think of all of the Angular JS and other toolkits and dev kits and all of that. Well, anyway, sorry. What seems required is efforts by people with a certain minimal understanding and interest in both areas. Yeah. Like at your leisure, when you have time, do read what every computer scientist should know about floating point numbers. So here we go. Let's take an example, a different function than before. And the function is slightly more complicated, maybe a y equals log sine of x squared. So we'll need two traces. The primal trace is in the forward direction, is from x to y, and then the tangent derivative can be computed in the forward direction. Tangent derivative, our directional derivative, we just discussed in another previous episode, is forward mode AD. Cotangent derivative, it's the reverse mode AD. It's what we are discussing now, slightly differently organized, but thankfully linear computation graph. Figure is thanks to Roger Silva. So we have x, then we apply the power, then to the result we apply the sign. So there are no branching, so it will be easy to follow what's going on. And then we apply the log, and then we produce the output. Ta-da, done. So we just followed precedence rules, and then binary and n-ary operators are allowed as long as we have a tag. You have seen a computation graph. It's the same computation graph your compiler constructs, but now we will do something else with it. Instead of computing the elements of our Jacobian or elements of our gradient one by one, we will compute them all at once. So for every given y in the output, we will compute the gradient of this yi with respect to x as a gradient vector dy of I dx1, dy I dx2, and so on, blah, 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 in one just pass. So y is the root, x is the leaves because we're going backward because it is reverse mode accumulation. So we have intermediate variables, z sub I in this case. So each intermediate variable we need to make those assignments when we an aside. This is actually a downside of backprop or reverse mode AD, because you need to store all of those intermediate variables. You cannot just get rid of z1 and then produce y. We need all of them, z1, z2, and z3. Why do we need them? We'll see. Well, there is another notion of a joint of x or a joint of z. It means the outputs y derivative with respect to that variable. So take any variable, any intermediate variable, say z3. So what is adjoint of this 3? It's dy by d3, z3. Let's continue the example. So we have our example. The forward computational graph is done. We went through all of the steps and we computed the output. let's go backward now. So let's compute the adjoint of Z3. So dy by Z3 is nothing but dy by dy. So adjoint of y is 1. We've started with this adjoint. So now imagine that we had similarly y1 and y2 as in the previous example. If we will set y1 to 1 and y2 to 0, we will end up computing the gradient or Jacobian transpose by um, a column of Jacobian transpose. Okay, first adjoint is down, we got it. Second adjoint, z2, is nothing but dy by dz2, but what is it? Well, it's dy by dz3, and we have it. It's z3 adjoint, which is y adjoint here, which is 1, and dz3 by dz2. What is our dz3? Okay, so derivative of log 1 over z2, and that's what we got. And then the same adjoint of z1, it's dy by dz1, and chain rule again here, but we already computed everything, so z2 and uh, derivative of the sine is cosine, got it. And now we have adjoint of x, and we already computed the previous part, so well, and well, I mean dy dy by dz1. So yes, and we're computing dz1 by dx, x squared to x, done. So essentially, we've computed one by one all the chain rules, the chain rule, and in the end, we've computed the x. And this is one-dimensional example. Uh, I made it easy for you. Well, actually, Rogers, but we can kind of combine and compute it all together. And so interesting, you can use the point of this example and the point of this lecture is not to give you in one sitting, give you a full course on everything about automatic differentiation, about AD. The point is to introduce you to the notions, and then you will figure out in your homework and later in your life and career how the little details of it work uh, of AD. But right now, PyTorch, Chainer, um, those two kids, they are doing truly algorithmic differentiation and TensorFlow and the late Theano and other similar packages, they're doing something else. Why am I saying that? So the dream of differentiable computing is, and AD supports it and fuels that dream, is that all of the, like you're evaluating while computing, like you're going backwards through your computation trace. That's why the word trace in the last slide. So you're evaluating your derivatives and keeping your intermediate values depending on how you went forward. So you're running your code and if then else statements, forward loops, branching, and everything is naturally supported. Next iteration, you go through a different branching in the if then else statement. Doesn't matter, you can still differentiate that. And when I'm saying again, note what I mean by differentiating. I don't mean you're computing the function, the derivative, but you can compute the value of the derivative of this function that took that particular branch. That's a different function right now. Nevertheless, you have the derivative value as well. So you can keep building um, natural expressions of numerical um, programs, and the derivative will be computed automatically. The numerical value of the derivative will be computed automatically for you. Another um, application or interesting tool that probably was unexpected, but is that you can actually use reverse mode AD to manually differentiate functions. Uh, you can use this technique that's on the board, and that is in the first reference, Appendix 3. You can use it, you can use reverse mode ID to obtain a symbolic derivative manually. It simplifies the process of differentiation of a complex matrix function. Sometimes we need this for a paper, for a proof, to figure out what's going on, or to actually symbolically implement it in our code. And so reverse mode ID enables that manual computation, and or simplifies it hugely. Um, well, that's I think that's all for this lecture. You need to understand the difference between reverse mode ID and forward mode ID. You need to be able to um, compute derivative of a function in forward mode, and hopefully in the reverse mode as well. But forward mode would be a must, and you need to understand why the forward mode is directional derivative, and what does the reverse mode do. Um, Hopefully this is teaser for you to go and learn more about AD. It's one of the advanced topics that we cover in this class, but maybe it is not as advanced as underrated. Uh, Fun stuff. Thank you.